Recent aerial observations of the Arctic Ocean reveal a landscape increasingly defined by fractured flows and open water. Climatologists measure the health of this region using a metric called sea ice extent. This counts any ocean surface where ice covers at least 15% of the area. These satellite maps provide a daily footprint of the ice edge. Tracking this area from 1979 to present shows a steady retreat, culminating in the 2025 record low. Plotting this reveals a linear decadal decline. The total two-dimensional area is shrinking at a consistent rate. However, surface extent is sensitive to short-term weather variability. Surface winds can physically spread ice flows apart to cover more area, or a rapid freeze can create a thin layer of new ice that inflates the daily measurement. Tracking surface area alone provides an incomplete assessment of the ice pack. It omits the physical thinning of the ice, which suggests a more significant structural change is occurring beneath the surface. To calculate the actual state of the Arctic system, researchers must reconstruct the full physical architecture of the ice. This requires a three-dimensional model beyond the X and Y coordinates of a surface map. Researchers must integrate the Z-axis, the physical thickness, or total volume. The model also incorporates the ice's history, tracking its age and lifespan over multiple years. Obtaining these measurements is a complex technical task compared to the relative ease of taking satellite photographs of the surface. Integrating these dimensions allows scientists to distinguish the long-term anthropogenic signal from the noise of natural variability. The primary catalyst for ice loss is Arctic amplification, a process where the high latitudes warm at a much higher rate than the rest of the planet. We track this warming by comparing current observations against a fixed historical baseline from 1951 to 1980. This bell curve centers on that average, representing the zero anomaly. ERA5 reanalysis shows the global average temperature steadily rising above that mid-century norm. When we isolate data for the Arctic, the trend diverges. The region above 65 degrees north shows extreme positive anomalies, particularly during the boreal fall. This thermal forcing creates a scenario where the ice is simultaneously warmed by the atmosphere above and the ocean below. While these temperature records explain the retreat of the ice edge, they do not show the total loss of physical mass within the pack. Direct measurements of sea ice thickness are difficult to collect. Researchers gather data by manually drilling into the ice, providing precise but geographically limited samples. To fill the gaps between these samples, scientists use PO mass, a model that assimilates available physical observations to simulate the volume of the entire ice pack. This map shows simulated sea ice thickness from 1979 through 2025. Here, color intensity and vertical elevation represent the depth of the ice. The map distinguishes thin, seasonal ice from the thickest sections of the pack. These areas of multi-year ice serve as the structural anchor of the polar cap. Applying a threshold to this data allows us to mask all ice thinner than 1.5 meters, revealing only the foundational ice. Advancing the model to 2025 shows that this foundational ice has nearly vanished, leaving only small isolated pockets of thick mass. This data shows a transition from a solid, multi-layered shield to a thin surface layer that has lost its vertical mass and physical stability. Thickness is closely correlated with the age of the ice. In the Arctic, the oldest ice is typically the thickest. Climatologists monitor this using the EASE grid system, which tracks the movement of specific ice parcels over consecutive years. In 1984, the Arctic was dominated by multi-year ice, structures surviving at least 4 summer melt seasons. As we advance through the satellite era, this older ice is transported out through the Fram Strait, or melts as the ocean warms. The Arctic has transitioned from a stable environment of multi-year ice to a regime defined by thin, seasonal ice that forms and melts within a single year. The ice present in the Arctic today is younger, thinner, and lacks the mechanical strength of the ice pack from the late 20th century. To see the full scale of this change, we must evaluate all 3 metrics side by side. Here we have the two-dimensional extent, the simulated three-dimensional volume, and the percentage of multi-year ice from 1979 to 2025. Drawing a linear trend line through each dataset allows us to compare the rate of change for each physical property. When we superimpose these trend lines, the discrepancy is clear. The rates of volume and age loss are significantly steeper than the decline in surface extent. This extreme thinning makes the remaining surface extent highly vulnerable. Without the mass of older, thicker ice, the pack is more susceptible to rapid melting during anomalously warm summers. Two-dimensional maps of surface area omit the vertical thinning that has already occurred, obscuring a loss of structural integrity that is now measurable across the entire basin. The degradation of this ice mass shifts the heat balance of the planet, carrying consequences far beyond the high latitudes. The loss of three-dimensional ice mass changes how heat is exchanged between the Arctic Ocean and the atmosphere. Without that dense layer of insulation, the ocean releases stored heat into the atmosphere, which influences the trajectory of the Gulf Stream and alters the winds of the quasi-biennial oscillation. These changes contribute to broader atmospheric patterns, such as the warm Arctic, cold Siberia anomaly, where extreme heat over the pole coincides with deep freezes across the Siberian landmass. The stability of the Arctic system is measured not by the surface area of the ice, but by its thickness and its ability to survive over multiple years. The simultaneous decline in thickness, age, and extent represents an ongoing reorganization of the Arctic system that now influences global atmospheric and oceanic patterns.